Today we'll be going through some advanced geometry. However, the surprising fact will be that it is simply geometry for kids. You see, it's only for the 8th grade. But I bet that even if you are an adult, even if you have some relation to mathematics, maybe you graduated from some university, you have a degree, and you won't be able to solve 8.3, for example, in some certain limited amount of time. You can take 45 minutes, 60 minutes, 90 minutes. In my experience, most of people won't be able to solve, for example, 8.3 or 8.2. And moreover, you shouldn't even restrict yourself with the knowledge of 8th grade, because probably 8th graders, they don't know what are sines and cosines. You shouldn't restrict yourself. You can use all your knowledge in geometry here, and even in this case it will be pretty difficult for most of people to solve these problems. Where do they come from? They come from national geometry Olympiads. In some countries, besides math competitions of the national level, they have geometry competitions of the national level, and it is an example of one. You see, you have for 8th grade 4 different problems. Probably kids are provided maybe 4 or 4.5 hours to solve it. Also, second day, also 4 different problems. The level of difficulty increases a little bit on the second day, as usual. Also, there are problems for the 9th grade, also first day, second day, and finally for the 10th grade you have some problems for the first day and some problems for the second day. For 10th grade, it's really already an advanced geometry, almost the level of International Math Olympiad. It's the great way to practice, because for myself, I always love to practice mathematics and geometry in the most simple and convenient way, just to do it by practice. For example, I know that I have 3 hours of my time that I can dedicate to solve something, and instead of going through some long books, I open some paper from recent years, and I simply turn on stopwatch like here, and I know that the next 3 hours are dedicated to solve these problems. And I will tell you, even if you are an adult, even if you know math, to use these 8th grade papers, it's a great way to practice geometry. Some of these problems, they can be really pretty advanced. So 8th grade, but nevertheless it's not accessible for most of adults. Below this video I will provide you the website, and you can download all these papers and materials for free. For example, you should click here on some of the recent years, 2018, 19, 20, and here you need this one, final round, and here you need this problems PDF and solutions PDF. And if you click to problems PDF, you will be able to open the materials from the certain year of this National Olympiad on Geometry. So even if you start from the 9th grade or 8th grade, it is still great practice on geometry. You can be even at school, at high school, still, if you start from the 10th grade, it's for the most advanced students. It's for very smart people who practice a lot. So 9th grade is also a great level of difficulty. So let's solve, just as an example, one of these problems. I will provide my own solution. The official solution is even simpler. So let's go to the 8.3, and I will explain what this problem is about. Here is a picture. We have a triangle ABC. You draw medians AD, BE, and CF, all the medians. You take midpoint F and you reflect it with respect to one median, with respect to BE, and you get, for example, this image Y. And you reflect it with respect to another median, and you get this image X. You look at these 2 narrow triangles. One narrow triangle is ADY and another one BEX. You need to show that their circumscribed circles have the same center. In other words, circumscribed circles of triangles ADY and BEX are concentric. Well, initially it looks a little bit advanced, and as you can see in this picture we have a lot of elements. So the great idea is to understand what is the pattern here, what happens. And what happens is that we reflect midpoint with respect to the median, and we get this image, and after that it's connected with the midpoint on another side. And it happens actually twice. It happens once here and once here. And of course it makes a lot of sense to look at this process closely, to separate basically this reflection, and to look at this segment dy, because dy is the side of one of your triangles that you need. Well, what is this dy? Maybe it has some special properties. If you have a good picture where the midpoints are real midpoints, where reflections are real reflections, you can see that dy maybe will be parallel to this median. It looks like this, maybe it's not. And if you have a basic experience in geometry, you immediately see that y is somehow suspended. There is just, you maybe need to connect y with some other points. And here the great idea is to connect why with the point A? Because you will immediately get this construction, this configuration where AYF is your triangle and BE is the line that intersects several sides of your triangle, and you will be able to use Menelau's theorem to find the ratio of these two segments. Let me explain you why we need it and what is Menelau's theorem. It is not really an advanced stuff, and it greatly simplifies for you the solutions of many complicated problems. You will need to go into advanced details if you use it. For example, you have a triangle, you extend one side, and you have a line that intersects the sides of your triangle. So it intersects this side, and the extension of another side. What Menelau's theorem gives you? It tells you that you need only to mark these 3 points of intersections, and after that you can get this formula. Formula is very simple. You start from any vertex and you will always jump from the vertex to the point of intersection and from the point of intersection to the vertex, and you will create this ratio x over y. X is the length of the segment, right? So x over y. Next, you are at this vertex now. You will jump from the vertex to the point of intersection and from the point of intersection to the other vertex times a over b times a over b, and finally times here you are on the last side of triangle and you will do the same process. Here you will jump from the vertex to the point of intersection, let's make it n, and from the point of intersection to the vertex where you started, n. So times m over n, and it is 1. So this ratio is always 1. What is the point of this theorem? If you know, for example, this ratio x over y, you know the ratio in which a line divides one side of your triangle. And if you know, for example, a over b, the ratio in which a line divides the other side of your triangle, you will be able to find mn pretty much immediately from this equation. So if you know the ratio in which line intersects two sides of your triangle, Menelau's theorem allows you to find the ratio in which line intersects the third side of your triangle. And this theorem, amazing, very useful. It allows you to avoid really difficult geometry, and it is super universal in terms of, you see, I started here and I went to this direction. It's not necessary at all that you need to start from some certain vertex. You can start from any vertex that you need. You can start from here and you can go to the other direction. And I can go n over m to b over a to y over x, and this product will be still equal to 1. It's not necessary even to start from this vertex. You can start from any other vertex you want. You can start from here and to go to this point of intersection to the vertex, from here to here, from here to here. The only thing that you need to go always on one side from the vertex to point of intersection, from the point of intersection to the other vertex. It is the main rule, but you can go to any direction and you can start from any vertex. And this theorem, it is so universal that even works like when the line intersects the extensions of the side of your triangle. So you can imagine that it doesn't intersect the sides of your triangle, but it intersects only extensions of your sides. So for example, let me extend the sides of my triangle. We don't need perfect picture here, just like this. I extended the sides and some line intersects not these sides, but extensions, only this. And Menelau's theorem works even in this case. So you can jump from here to the point of intersection. Just it's important to stay on the one side at a time. You jump from here to here, and then back from here to here, and then from here to this point of intersection and back to this side, and from this point, from this vertex to the point of intersection, and here, and this product will still be 1. So it's very universal theorem, and what it allows you to find. In many problems, for example, you see here, it will allow you to find this ratio, for example, this segment divided by this segment, because that's the only thing I know. You immediately see that here we have triangle AFY and BE intersects this side of triangle, and the extension of AF, and many ratios here are very well known. For example, I can start from the vertex A, and if I go from here to here, this ratio is 2 over 1 times, now I go from the F to the point of intersection, from the point of intersection to the vertex, it will be 1 over 1 times 1 over 1 times from the vertex to the point of intersection, and from the point of intersection to the vertex, so it will be m over n. This one is unknown, m over n, and therefore m over n, and it is equal to 1, of course, so I should write here that it is 1, and therefore m over n is equal to 1 over 2. In other words, we can rewrite, instead of m, we can write, for example, like y, and instead of n, we can write 2y. For example, this one should be y, and this one 2y. By the way, you obviously recognize that y over 2y, it is the same ratio for the medians. And here we have medians. It is a point of intersection of this median and this median. And of course, you know that this segment over this segment is also 1 over 2. So for example, if this is, for example, z, then therefore this one has to be simply 2z. It immediately tells you the next thing, that this triangle, small one, is similar to this bigger triangle. You see they have a common angle here, and you have the ratio of their sides like 2 over 3. It means that if these triangles are similar, this one and bigger one, then this segment is parallel to dy. If this segment is parallel to dy, therefore dy is parallel to this median BE. This is it. What does it tell you? If dy is the side of one triangle that you're looking for, and BE is the side of another triangle that you're looking for, they are parallel. The center of circumscribed circle is the point of intersection of perpendicular bisectors to the sides of your triangle. For example, if I look at perpendicular bisector to this segment, and if I look to perpendicular bisector to the other segment, as soon as these segments are parallel, perpendicular bisectors to them will have to be parallel. Well, let's look how it will be. Just let's make a picture just to understand what's happening here. We have one segment dy, so perpendicular bisector to dy will be some line. It is parallel to perpendicular bisector to this one. So another perpendicular bisector will be some parallel line. And similarly, you will show in exactly the same way that XE is parallel to AD. So that this segment is parallel to this median. And here, by the way, you see how important it is to make a proper normal picture. Because in my case, this segment is not like very proper. It should be a little bit larger because it's not like a good reflection. X should be a little bit like in this side. And because of that, it doesn't look really in my picture that XE is parallel to AD. So not it's very important because if you make picture like this, here I was lucky with this one, but here XE doesn't look at all like it's parallel to AD, but it really is by the same reason as we described. So, and we will get that these two are parallel, median AD is parallel to XE, and their perpendicular bisectors will be also parallel. So perpendicular bisector to another one, XE, will be parallel to this one. So let's draw a couple another perpendicular bisectors, and these are like parallel lines. So as you can see, and this, for example, this point is the center of circumscribed circle of which triangle? For example, this one, perpendicular bisector of this segment is this one, perpendicular bisector of this segment is this one, and this point of intersection is center of circumscribed circle of this triangle. Okay, so what is this one? It is a perpendicular bisector to this one, and this one, for example, perpendicular bisector to this one. But I'm just making the picture to understand how it may happen that these 2 points are coincide, because these 2 points are centers of circumscribed circles of these 2 triangles. And I know that perpendicular bisector this one parallel to this one, and it doesn't look like these points coincides, because this center of circumscribed circle is the point of intersection of like two lines, and another center of another circumscribed circle is the point of intersection of 2 parallel lines. So how does it happen that they coincide? It doesn't look at all, because you have like a parallelogram here if you extend. So it makes me make another assumption. Maybe these lines will actually coincide. Maybe perpendicular bisector to this segment and to this segment, they will be not just parallel, but they will be actually the same. It will be the same line, because if the same line makes a perpendicular bisector to dy and BE, in this case everything will be great. Look, if this one has the same perpendicular bisector as this one, then these two triangles have a common perpendicular bisector, and this line and this line have also common perpendicular bisector. It means that your triangles, this one, this narrow ADY and BEX, they have two common perpendicular bisectors. Two lines that are perpendicular bisectors are actually the same lines. And of course, their point of intersection will be the same point. It means that we want to show that this line coincides with this one and this one coincides with this one. How should we do it? Well, look, dy is parallel to BE. We want their perpendicular bisectors to be like the same line. It's our assumption. Maybe it is true, maybe it's not. Let's look. BEYD is a trapezium. No question about it, because this one is parallel to this one. It is a trapezium, and in which case, in trapezium, you will have that perpendicular bisector to one base is the same as perpendicular bisector to another base. Well, obviously, only in one situation, if it's isosceles trapezium. If lateral sides BD and EY are equal, if these two sides are equal, in this case the trapezius is isosceles, it is like symmetric, and you can make a perpendicular bisector. It will divide this trapezium into two equal portions, and in this case that's everything you need. So, but is it true that EY is equal to BD? Let's look. EY, Y is a reflection of the point F. So it means that EY has to be equal to EF, inevitably, because you have two equal triangles here. This triangle is equal to this triangle. EY equal to EF. So this one is equal to this one. But what is EF? EF is actually a midline in your triangle ABC. It connects midpoints. Therefore, EF is a half of this side, but half of this side is actually BD. So BD, half of this side, is equal to EF, and EF is equal to EY, and therefore BD is equal to EY, and therefore lateral sides of these trapeziums are equal, and therefore it is an isosceles trapezium, and of course these bases, dy and BE, they have a common perpendicular bisector. And it concludes the solution of our problem. As you can see, there was just nothing super advanced. Of course, I used Menelaus theorem for my own convenience, but you can get here another solution even without it. It's just, for me, I just love to use it when I see some configurations that allow to do it, because it allows you to avoid complicated steps. Maybe you can find your own solution, and it is the problem for the 8th grade, and many children from the 8th grade, they really successful solve problems like this. So it's just an amazing level, and it gives you like the bar to which you should stick, because if you solve some geometry from AMC or AME, usually it's very simple stuff. Classic math competitions, they usually focus on geometry like this, and this geometry, as you can see, it's much more complicated and it's way more interesting. So this is it. Thank you and have a great day.